working our way through step 5, which is the multiplication axioms. And we've done M1 through M4. Now we're on M5, which is the inverse, which means that for every alpha in R plus, there exists a beta such that alpha beta equals 1. That's what we're trying to prove. So we're looking at beta. We've defined beta the same way that we did, or in a parallel way to what we did with the addition, which is that beta is the set of all p such that minus p minus w is not in alpha. That's what it was for addition. So for multiplication, actually, this isn't what it was. For multiplication, it was p such that 1 over p times 1 over w is not in alpha. Okay? So then, with this definition in mind, we ended the last video by looking at beta and proving that it is in fact a cut. So we proved the 3 properties of cuts, which are that they're not empty. If there's one element that's in the cut, then everything then everything less than that element is also in the cut. And for any element in the cut, there's going to be another element larger that's still inside the cut. That's 3. So now we need to prove that beta, in fact, as we've constructed it, will be an inverse for alpha, meaning that alpha times beta is going to equal the multiplicative identity. So the first part of this is not going to be hard, and I'll get to that in just a second. But this video is going to be a little different than normal because I'm actually going to fail to get this proven in this video. And if you remember, I showed you in the last video that Rudin says that the proof of the multiplication axioms is so similar to the addition axioms that he doesn't even bother to show them. And I think that he actually didn't even try, because they're not just not similar, but they're actually, as far as I can tell, not possible to do in the way that he did the addition axioms. So what I'm going to do this video is try to apply what we did in addition to prove the multiplicative inverse and see how far we can get, see if we can do it. And then in Rudin's book, one of the books that he refers to in his bibliography is by a guy named Landau, who also constructs the real numbers from Dedekind Cuts. So what I'm going to do in the next video is go through Landau's proof and see if we can understand his proof in order to finally finish this. So we'll see how that goes. And I haven't looked at this yet, so I think what I'm going to do is just do it live.
We'll do it live!
I'm just going to open it up, read it, and see if we can figure it out together while I'm doing it here. So we'll see whether we can do that, and then if not, we'll go back to the drawing board and figure something else out. But for now, I'm just gonna show you what happens when we try to do it the way that Rudin did addition and show that it doesn't work. So first of all, so we need to prove that alpha times beta equals 1. So always, we've done this a few times now. If you need to prove that 2 sets are equal, the way to do that is to prove inclusion in both directions. So first we're going to show that alpha beta is a subset of 1. Then we're going to show that 1 is a subset of alpha beta. Now the first part is actually not that hard. I think I can do it right here. So we're starting with an element of alpha beta, and we're going to show that that's also in 1. So if R is an element of alpha and S is an element of beta, then 1 over s is not an element of alpha. So first, why is this? This is because if s is in beta, that means by definition that 1 over s times 1 over x is not an element of alpha for some x greater than 1, right? That's our definition of beta. So if x is greater than 1, then x greater than 1 implies that 1 over x is less than 1. That means if we multiply something smaller than 1, it's going to be smaller than what you're multiplying. So that means that implies that 1 times s times 1 over x is less than 1 over s. So that means that that's what I wanted to show you. That means that 1 over s is not in alpha by b. Because b is our reformulation of 2, which says that if we know that one number is not in a cut, then anything bigger than that number is also not in the cut. So if 1 over s times 1 over x is not in alpha, then 1 over s is also not in alpha. Okay? Okay, I can finish it here in this little corner. So that means that r is less than 1 over s, because 1 over s is not in alpha, but r is in alpha, and that is part A. If you have one element that's not in a cut and another element that's in the cut, the element in the cut has to be less than the one that's not in the cut. So r has to be less than 1 over s. So that means, so we have that r less than 1 over s. So that means that if we just multiply both sides by s, we get rs is less than 1. That means this is an element of alpha beta. So alpha beta has to be a subset of 1, right? This is an arbitrary element of alpha beta, and no matter what it is, it's going to be an element of 1. That's what we needed to prove. Okay, that's all there was to this one. Now we have to try to prove that given any element of 1, it's going to be a subset of alpha beta. That's where we have trouble. So for 2, need to show that 1 is a subset of alpha beta. So what we're going to do is try to mirror what we did with addition and see what happens. So remember with addition, the way that we proved that 0 was a subset of alpha plus beta was to take a v less than 0. In other words, it's an element of 0 star. Then we choose a w equal minus v divided by 2. So in other words, the opposite of v divided by 2. Then we showed that using the Archimedean property, if we have a cut here, there's some n such that nw is inside alpha and that n plus 1w is just outside of alpha, and then that means that n plus 2w is also going to be outside of alpha, right? So then using this, we let p equal minus n plus 2w. And remember what we're doing here is, in order for p to be in beta, we need to be able to take the inverse of p. So p is going to be over here somewhere, we hope, in beta, right? Beta's down here. So p is over here. We want to be able to take the inverse of p and then subtract w from it and still be outside of alpha. That's the definition of beta. So this allows us to do that. So we have that p equals minus nw minus 2w. So then we can show that this is, what we need to show is that this is in beta. Remember, we're still just doing it for addition here to show what we're trying to mirror. So we take the inverse of this, so minus p equals nw plus 2w. And then here's where it's interesting. This is the point of what we did here, or the first half of the point. So then if we subtract w from both sides, we have that np, or the inverse of p minus w equals nw plus 2w minus w, which equals w, which equals, so then if we take out the w here, we have n plus 1 w, and we started with taking an n that says that n plus 1 w is outside of alpha. We already know that that's outside of alpha. So what we just showed is that minus p minus w is outside of alpha. That means that such a w exists. That means that p is in fact an element of beta. Now, what we're really looking at though is we want to relate this to v. So let's look a second more. We have w equals minus v over 2. If we multiply both sides by 2, we get 2w equals minus v. That means that v equals minus 2w. So if we have up here that p equals, from this, p equals minus n plus 2 w equals minus nw minus 2w. If we add nw to both sides, we get that p plus nw equals minus 2w, which we just said equals v. And what is this? We started by saying that nw is inside alpha. We just showed that p is inside beta. That means that this is alpha plus, or well, beta plus alpha, which we know that they're commutative, and that this equals v. So we just proved it, because we started with an element of 0, an arbitrary element of 0, and we showed that no matter what that element of 0 is, it's also going to be an element of alpha plus beta. Okay, so let's try to go through the same thing with multiplication and see what we can do. So here, instead of 0, we're going to choose a v which is less than 1, meaning that it's an element of 1 star. Now, what w was, it was, for addition we had some v that was less than 0, and then we took the inverse of it, so it was on the other side of 0, and then halfway between 0 and minus v, right? So this is minus v over 2. So it's basically the inverse of v and then halfway closer to the identity. So what we're going to do here we have 1 instead of 0, and we have a v that's arbitrary. So we want the inverse of this, and halfway is close. So there's another complication that I'm not going to go into in a lot of detail, but there's even a confusion here about the addition is just way more symmetric than the multiplication. So it's unclear from this. Does this mean you take the inverse of v and divide it by 2? Or does it mean that you take v and divide it by 2 and take the inverse of that? In addition, those two things are equal. But in multiplication, they're not. So if what this means is you take the inverse of v and divide it by 2, then this would be 1 over v, and then you divide that by 2. You want to get halfway between them, so it would be 1 plus 1 over v divided by 2. That's a number around here. Or maybe it means you divide v by 2 and then take the inverse, in which case we're taking this number, we're taking the average there and taking the inverse of that. That would be 1 plus v divided by 2. These two are not equal. One's a little closer to 1 than the other. Neither one of them work. So I'm just gonna, I'm going to look at this one, and we're going to forget about this one because it's just even more complicated. So if we set W equal to 1 plus V divided by 2, no, not W. So 1 plus V divided by 2, I'm sorry, is this number here. Then we want the inverse of that. So W we want to equal the inverse of this, which is 2 over 1 plus V. Okay, so we're going to try this number and use this number instead of this and see how far we get. Now, the next question is, do we want to use these values? This is how it was for the addition. We had NW, N plus 1W, and N plus 2W. That's what the Archimedean property allows us to do. Let's see what happens. So we have that NW is an element of alpha, N plus 1W is not an element of alpha, and N plus 2W is not an element of alpha. Okay, so then we set P equal minus N plus 2W. And then we come down here, maybe this is okay, minus N minus 2W, and then, I'm sorry, minus NW minus 2W. But then in this case, we want the inverse here. So this just isn't the right way to do it, right? Because we're not doing enough to move over to multiplication. Because if we had 1 over P, if we took the inverse of both sides, and we end up with 1 over minus NW minus 2W, and then we're going to try to multiply 1 over W by both sides, that definitely won't work. So first thing is this isn't the right way to do it, and this isn't the right way to do it. So what I want to do is instead say, let's get on a new page. Instead say that if we have alpha, there's a version of the Archimedean property that will allow us to say that W raised to the n is inside of alpha, but that W raised to the n plus 1 is outside, and W raised to the n plus 2 is even further outside. Now, I haven't proven this yet, but I think we can, because I can show that W is positive, which means that if you, and greater than 1, which means that this is always going to be bigger, so there has to be one that's just inside of alpha and another one that's just outside of alpha. So this will clearly work, but I'm not going to prove it yet because we're not going to need to, because we're going to get stuck before that. So let's look at this. So that means that Wn is inside alpha, Wn plus 1 is outside alpha, and Wn plus 2 is outside alpha. So now, let me tear off this page so you can. Okay, so now I'm gonna just go through here, but we're gonna do everything with exponents instead of addition. So what we want this time, now what we're trying to prove is that 1 is a subset of alpha beta. That means that we're going to start with something inside 1, which is V, and we're going to show that it's inside alpha beta, which means that whereas here we had P plus NW was alpha and beta. So in this case, we want it to be P W raised to the n, right? W to the n is inside alpha, and then we're going to show that P is inside beta. So this would be an alpha beta. So if we can show that V is a subset of this, then if we can show that V equals this, then we've shown that 1 is a subset of alpha beta. So we'll set, so we have the Wn plus 2. So we're going to set P equal to the inverse of that. So we're going to say P equals the inverse of NW of w to the n plus 2. But in this case, it means like this. So this is basically 1 over w to the n plus 2. Okay, but I'm just going to leave the minus here. So what if we expand this now? We have p equals w to the minus n times w to the minus 2. Okay, that's okay. If we take the inverse of both sides, we have that 1 over p equals, now it's w to the n, right? Because it's just the inverse, the multiplicative inverse means that it's the opposite sign for the exponent. So it's w to the n, w squared. And you see that's this. Now, if we multiply the inverse of w by both sides, we have 1 over p, 1 over w, equals w to the n, w squared, 1 over w. That means that these cancel out, one of these cancels out, and it's just 1. So we end up with w n w equals w n plus 1. That's what 1 over p, 1 over w equals. Wow, we're doing great. Because we know we started with w to the n plus 1 is outside of alpha. So that means that 1 over p times 1 over w is outside of alpha. That's great. That means that p is an element of beta. So far so good. So what we have to show now is that v equals p to the n plus w. So let's look at v again. So we defined v as, no, I'm sorry, we defined w as 2 over 1 plus v, right? We went basically halfway between 1 and v, halfway between and the inverse, so over here. Looks good. So if we solve for v here, we multiply both sides by 1 plus v, so we have w 1 plus v equals 2. And then distribute that, we have w plus vw equals 2, vw equals 2 minus w, then divide by w, and we get v equals 2 minus w over v, over w. Or you can rewrite that a little bit, equals 2 over w minus 1. Okay, well, now the problem is, remember, what we needed to do was we need v to equal the thing that we need v to equal the thing that we ended up with over here. Because what we want to do, so let's see, okay, so what the next thing is, what we have here is, we have that p equals, let me go back here. We have that p equals w to the minus n plus 2. And then what we did here is we moved the nw over to the other side, and then we were left with v. So to do that with multiplication, first expand it again. So p equals w to the minus n, w to the minus 2. Then if we multiply w to the n by both sides, we have that p wn equals w to the minus 2. Now that's great. So far, that's exactly what we ended up with here. P plus nw equals minus 2w. That's the equivalent here of pw to the n equals w to the minus 2. Now what we need, the last step, is to have v equal 2 minus 2w, or here, this needs to be equal v. Problem is, we looked, and what we ended up with actually is that v equals 2 minus w over w. So there's no way that that equals w to the minus 2. So what that means is it's definitely not as simple as simply following the same proof and you end up with the equivalent answer popping out. It doesn't work to just pick, to do everything in parallel. What this implies is what we have to do here is pick a better number for v. We need v to equal w to the minus 2 to begin with. Then when we go through all this, we'll be able to have it equal the p w to the n. Okay, so let's start with that. Let's see what we need it to be. Because what we did before was we had that w equals v over 1 over 2 over 1 plus v. What we want is for v to equal w to the minus 2. So what does that, so let's solve for w. So if v equals w to the minus 2, let's take the inverse of both sides. So we have 1 over v equals w squared. And then you take the square root of both sides, and we have 1 over square root of v equals w. Now, I just want to show you that if w equals the square root of v, then v equals w to the minus 2. And if we let that happen, then we do in fact get the answer that we want. Because we have that p, everything else is the same. Nothing else here is a problem. Everything works. So, and we get through and the answer that we want falls out. We have p equals w to the minus n plus 2. So p equals w to the minus n, w to the minus 2. Then if we multiply both sides by wn, we get p wn equals, these cancel, w to the minus n, w to the n. Those cancel and we end up with w to the minus 2. And then we started with that we defined w as 1 over v, the square root of v, which means that v equals this. This is v. That means that in this case, if we start by setting if we start by setting w equal the inverse of the square root of v, then we've got what we want. Because then what we just showed is that v equals p w n. This is in alpha, right? P is in beta. This v is an element of 1. That means that you start with any element of 1. That same element is in fact in alpha beta. That's what we want. Okay, looks good. Can we do this? No. V is a rational number. This just doesn't exist. The chances of v, the square root of v existing in the rational numbers is next to nil. That's the whole reason that we're doing this, because the rational numbers won't work with square roots. So this just isn't going to work. We're going to have to figure out some other way of defining what w is. So I just wanted to show you, my next brainstorm was, I thought about what is it that we need here. So we have 1, and we have some arbitrary v less than 1. Now, we can't just take a number halfway between, because what we need is this number squared will be inside of v, between v and 1, the way that it was with addition. It has to be something. What we want is for it to be the square root of v, which is over here somewhere, right? No matter how small v is, there's going to be a square root still that's between these two. If v is less than 1, then the square root of v is going to be bigger than v. Well, actually, I can show that easily. The square root, we've done this a couple times. If the square root of v is less than 1, then you multiply both sides by the square root of v, right? This equals v. So v is less than the square root of v is less than 1, okay? So if v is less than 1, then the square root of v is going to be bigger than v. So what we want is this number. If we had this number, we'd be all set, because then we could just set w equals 1 over square root of v. But we can't do that because this number probably doesn't exist. So what I thought was, well, what we really need is any number in here that will, because any number in here, if you square it, it's going to be less than v. So if this is w, then this would be w squared. That's good enough, because if we can show that p to the wn, if we can show that v is in alpha beta, then we can show that anything between bigger than v but still less than 1 is also going to be in alpha beta. As long as, and so what we need is that it just be smaller than the square root of v, so that then the w squared will land inside the 2, and then we can always make v arbitrarily small. So whatever this is, we can make a smaller one, then we can find a smaller w squared, and then we're done. So that was my brilliant attempt at proving this. And I got all through it, I wrote it all down. The big question that's still left unsettled here, though, is that if you have the number square root of v and 1, we know that there's always going to be a rational number in here. We've actually proven this but then again, we've proven it with real numbers. So again, this is something else that we're going to have to prove in order to make this work, because we can't prove it by using real numbers. We can't talk about this number because it doesn't exist in the rationals. So we know this is true. We know there's going to be a rational here. But anyway, after proving that, so there's basically two things that we need to prove. We need to prove that there's a rational number between the square root of v and 1, and we need to prove our Archimedean property with exponents. And then I thought that we'll have it, because we can always basically squeeze v. No matter how small v gets, we can always find a w in here such that the square is still greater than v, and everything's done. And when I got all done with that, and I was just sort of looking over it again, I realized that this squeezing doesn't work at all, because we're not actually talking about v. All I'm proving here is that for any number v, we can find a number w that's greater than the square root of v, such that the square of that number is greater than v. But then what we're actually talking about in the proof is w squared, not v. So this number, of course, is a rational number. But we haven't shown that v is an element of alpha beta, because this isn't a square. So what we've shown is that for every rational number that is a square, this will be true. But we didn't actually show for an arbitrary v that this will be true. Because if v isn't a square, then we don't know whether it's going to work or not. We can tell that it would intuitively, but we haven't proven it. So that's as far as I got when I decided that what I think I've shown here is that there is, I've been saying a few times as we've doing these last few videos that this is way harder than proving the addition. I actually think that's too strong. I don't know whether it's harder, but what I think that I've proven here is that it is not similar to addition at all. Doing it the way that we did addition is simply not going to work. The same methods are not going to work. And I think I've demonstrated further that Rudin didn't even look at it, because if he had, he can't possibly have made that claim that, hey, I don't even need to show it because it's so similar to addition. No, it's not. It's not the same thing at all. So what we're going to do next time is we're going to look at how Landau did it. I know that Landau proves it for real. So we're going to look at his proof and see if we can prove it his way, which I think is going to be a completely different method from what we've done here. And then we'll see where that takes us, and then we'll move on. Hopefully we'll be done with this, which Rudin basically punted, and I don't know, man. It's really easy to write a comment like, oh, it's so easy, I'm not even going to bother proving it. And I've said this many times, that's why you end up getting caught when someone actually does look at it and they're like, I don't think you can do that at all. That's what happened to Wiles, and why Wiles ended up not getting credit for the proof, because he didn't actually do it. Because he thought he did it and he hand waved, and that screwed him up. So, okay, so next time we'll go through Landau's proof, and I'm going to do that in real time and see if I can read it and figure out what it's saying at the same time, and then we'll go from there.
We'll do it live! Fuck it! Do it live! I'll write it and we'll do it live! Fucking thing sucks!
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.